So we are going to start with this seminar. And before introducing the speaker, I just want to kind of remind the students if they need any certificate of attendance to the seminar, please remember to sign in the document that is on the bench before you leave. So with this, thank you everybody for being here today. And it's my pleasure today to introduce our speaker, Javier Pérez Carvajal. He's a Ramón and Cajal researcher here at our institute. And he holds a PhD in chemistry from the Universidad Autónoma de Madrid, but he actually made the experimental work here at ICMM under the supervision of Pilar Aranda and Eduardo Ruiz-Gizki. After that, he moved as a postdoctoral researcher, first at ICN2 under the supervision of Professor Maspoc, and then he moved to France at the Sorbonne University with the supervision under the supervision of Professor Christian Serre and Bouquet Syria, working actually in the interface between two departments, chemistry and physics. So he had the opportunity to adjust his language to communicate to both chemists and physicists. He is working with a plethora of materials. Actually, his research now includes the integration of two-dimensional and porous materials like metal organic frameworks, mixins, clay-based nanocomposites. He has an emphasis on the fabrication of sustainable fabrication methods, but also on industrial scalability, because his research is actually fundamental, but also he's also interested in the industrial implementation of the results. He's actually collaborating actively with groups around the world, in Europe, but also in Asia, and involved in many projects. So the floor is yours, Javier.
Thank you very much. Thank to all of you for coming and letting me to share my passion with this kind of new material, that they are already 30 years old, metal organic framework, that we can consider as a new paradigm in material science, and we are moving from the initial application or target that we have in the beginning, that are molecular response, so porous material. And then now we are moving forward, and they are entering in a new concept that is not totally defined, that is quantum materials. So I will try to give a fast overview on the historical evolution of this kind of materials. So first, we need to start by what is a nanoporous solid. So it's part of the condensed matter, and when we consider that subsection of condensed matter, we can consider a non-porous solid, like dense material, okay, or this kind of material that presents some cavities inside the structure with different size, that we just call it pores. This kind of pores can be in different range. That can be in the nanometric range or even angstrom range, and then we call it microporous material when it goes up to 2 nanometers. When they move from 2 to 50 nanometers, we call them mesoporous materials, and everything that is over 50 nanometers we consider as macroporous material. In metal organic framework, we will move in these two kind of porous material that are microporous and mesoporous. These kind of materials are typically the feature that they present is the possibility to host some molecules or small atoms that can be ions inside their structure, so we can modify. They become something different, and we call it adsorption process. Okay. And they are also very common in separation process, because we can block the pass of some species and let the pass of another. So it's become in the separation process, interesting for separation process. Then porous material are historically over us forever. So we use as human natural clays to make this kind of application, absorption, separation, and so on. They are easy processing. They are still interesting, not only but because they are really easy process. We make pots forever. There are 2D materials, never mind this, and it has been used since all the human history, and it's the most material that is applied by the industry, and even though the porosity, the value that we give is the square meter per gram that this material presents, they are very low compared with the new materials that we can prepare. They are around 20 square meter per gram. In 1 gram, we can have a cozy apartment of the downtown, okay? So it's enough sometimes for everything, or it should be in nowadays. Then we move to zeolites that we can play tennis inside 1 gram, okay? They are around 300 square meter per gram typically. We have some highlighting development inside ICMM, so they break all the records. But typically we move in that range. They are natural origin, but we can also prepare synthetically. They are prepared by thermal synthesis, okay? So with zeolites, we can get access to different topologies, depending on design of the material, the precursors we are using, and so on, and the chemicals, the template, the organic molecule that we are introducing in the system, we can start making different topologies. Then we move to mesoporous solids and activated carbon. There's a move forward in terms of porosity. They are typically over 1,000 square meter per gram, so an indoor court for football is nice. And they are not crystalline. They are not topologies inside, so we lose one degree of freedom in that system. And the composition, we still are attached to silica or carbon. And then what popped up in the ending of the last century was the metal organic framework that always made by the combination of a metal or a group of metals that we call cluster that are linked by organic molecules to generate 3D structure or extended structure, because we can find 3D materials but also 2D materials depending on the design of our components. What are the components that we use to prepare metal organic framework? We have metals, so it's reported metal organic framework for almost all the metals that we can find in the periodic table. And we need to extend, so we use organic molecules that are D-topic, means they have 2 points that we can anchor to the metals. Tri-topic, tetratopic, there are geometric constraints, so we can extend in the 3D space our atoms and in a fixed position. Why I am saying that? Because we have different kind of, well, all of them are called coordination compounds, okay? And MOF are inside that family and inside the subfamily of coordination porous polymers, giving networks that are organic linked. And they should be porous. So there are 2 conditions in the definition of metal organic framework as part as coordination polymer that are crystalline, means all atoms are defined in the space, and they are porous. We can host something inside its structure. So if you have something that is a coordination polymer but is not porous, it's not bad, you have a coordination polymer. If you have a porous system that is not crystalline, it's fine. But as we define, this kind of system is like this. When it starts, we prepare it by thermal methods. And little by little, we extend the way that we can prepare to another strategies that can include electrochemistry, that we can include hydrothermal. We move forward out of the solvents and we try to make it in water for the sustainability. Also microwave to make it shorter. We can use templates, sonomechanical, ionomechanical, spray dryer, and finally, in the last decade, we moved to flow chemistry. Why? Because we can make it in continuous mode, and this material was starting considered as bulk material. We want to use it as powder, massive powder, for different application. What are the first application? Well, of course, it was given the Nobel Prize this year to this kind of material, especially related to the possibility to host water. Okay, this is a bit counterintuitive because at first you say, okay, you have coordination polymer here, and this is very weak for the interaction with water. But we will see that the community make it evolve, and then they become stable. These material are topological material, are defined by the crystalline structure, and we can get access to different crystalline structure in function of the nodes and the linkers that we are selecting, depending on the orbitals of the coordination of the metal. It can be tetraedric coordination, it can be planar. We can link it with a linear molecule. We can link it with different combination of geometry, so we can get access to different topologies that give us different kind of material. Okay, As the versatility is high, the way we label, we name them, is also complex. So the first thing that people like is scared well, the first block in the entrance to the thematic is what is this MOF and why it's called like this. So mainly are related to universities. This means Hong Kong University, and it's called level 1. Some of the labeling is coming from the zeolites. And it's moving forward, but this is still complicated with UPAC terminology. So sorry for that, but we are still moving like this, and it's hard to come back to another kind of labeling to the MOF. Okay. They have another feature. They are reticular materials. They are not only MOF. There are other compounds like covalent organic framework, for instance, that are reticular materials. What means that we can select one molecule with that one length. And we will have one topology and one structure, one solid, one porous solid. But as you can depict, this molecule, we can change it for that one. And our lattice is going to change. The topological simplification is going to be the same. We have the same hexagonal, but our material is going to be not totally different, but widely different. For instance, in terms of porosity. If we have small pores, we will have a surface area. If we move forward to bigger pores, the surface area will be increased like in an insane way. That's why metal organic framework become world record in materials, in absorption, in porous materials. And inside 1 gram, we can play rugby, not even football. It's even bigger. So world record is by Cajal in Dresden, and it's around 8,000 square meters per gram. Of course, this material disrupt everything because most of the applications are related to the surface area that you expose. And once you break that limits, you are order of magnitude above. So they become interesting for sure for gas storage and separation. But it opened also another kind of application like, drug delivery. We can make it biocompatibles. It was a huge impact in energy conversion, optoelectronics, and conductivity in different fields. So just to come back to the overview, this is the freedom of the degree of freedom that we have with metal organic framework. We have topologies. We have that can be different. We have secondary building unit that can be single atoms or clusters of metals, and different organic linkers with different nature. So chemical nature, and it will provide different pore environments and geometries of pores. On top of that, we still have particles. So these particles can be in the nano range, in the micro range, or in the millimetric range. So we will have the feature of nanoparticles or from single crystals. We can arrange them in monoliths, or we can make continuous films or even complex shapes because we have nanoparticles. So these are the main degrees that I will try to show at the end that are expanding nowadays. Historical overview. We ordered metal organic framework by generation. They are defined by Kitagawa. And we are assume like this. We all assume like this. So first generation was MOF, where the host-gas interaction destroyed the structure. And this was coming with the black legend of metal organic framework. We all know they are not stable, okay? Keep it like this. So once we have the interaction with the host, the lattice get destroyed. So this generation, even super important, was really fast overpassed by the second. The good thing for, especially for people from absorption, is that we get super funny isotherms of absorption. Why? Because we have one material that is completely moving, and sometimes in a reversible way, or semi-reversible way. So in absorption, we were very used to type 1 isotherms, everything go in, and then you are flat, nothing else happen. And once the lattice is moving, so we have tons of events, so we put the focus here. But we move fast to the second generation, and then it starts changing everything. In the second generation, the lattice get stable, it's rigid, okay? So once we can put in or out one gas, that can be nitrogen, can be oxygen, can be hydrogen, can be organic molecules of different size, can be drugs, can be whatever we can put inside. The porosity, as I told you, we can vary. We can make it super small, we can make it bigger, so it gets access to really very different species. And it can be single atom or multimetallics. Single atoms are a bit more weak, but not always. And then multimetallics that come around here. And then here you can see the historical evolution of the field in terms of structure, crystalline structure reported, that is in the maximum and it's coming down. And we can say, okay, thematic is done. No, we have huge amount of MOF, okay, as you can see. And here is a change with TIF and UIO66 especially, that become stable to water, so material scientists come to the field and it develop the increase of number of publications related to this material start increasing. So we have a threshold there where it was out of pure crystalline topic, pure absorption, more related to material science. And okay, just we have high porosity, we have high surface area, we can tune the pore, we can control the pore geometry, we can change the inorganic unit, we can change the organic ligand and so on. So what is the first thing that we have to do with this material? Storage of gases. It's a main topic as it was coming from adsorbents. So this field is really on development all the time. And we can simulate also this material because we have defined position. So IA enter and little by little move. Nowadays, you can see in that graph, each point is a metal organic framework, different one, that are experimental sometimes or only hypothetical MOF. And then we compare the volumetric capacity with the gravimetric capacity. Like this, we have a table where we can decide what to do, what to prepare, what to scale up, and where to what material is selected to go forward to industrialization, okay? And this is the moment of molecular sponge, we can say. As you can see here, we have MOF5 in the right side, okay? All these spheres are the space that we have to host the material. It's not the nanoparticles. It's the first thing I thought when I see really like 15 years ago, this kind of representation. And as you can see here, we have the same, but we modify this molecule for that one or that one. Okay, so from here to here, the pore is going to be bigger, and of course, the environment of the pore, the chemical environment, is going to be totally different. So there are is a reticular MOF20, this subfamily. Okay. After that, I will focus on one kind of material that is a theoretic imidazole framework. So it's imidazole-based materials, and it comes at the same time as the definition of MOF. Maybe Felipe knows it better. There are single atom metal organic framework. In that case, it will be zinc, and then we combine, for instance, with methylimidazole, and we have the archetypical CIF8, okay, with this structure and unit cell. If we change to this other molecule, we have CIF7. Sometimes they are just labeled by order of preparation. Okay, so they label like 7, 8, 9, 10. And it's a bit confusing because if we change this thing for a cobalt, we go to the same structure, but with cobalt, the isoreticular MOF, and we call it CIF67. Okay. If we change this imidazole for an aldehyde, we go to CIF90. Each of them is going to have slightly different properties, and for sure, stability for environment, particularly water, that is the more relevant in Earth. So I will focus on what can be done with CIF8. CIF8 is interesting because it's one of the first MOF that we really assume that is stable in water. So people start developing hardly, and we can find different reports of this material prepared by different groups with same properties and so on. So it becomes robust and verified synthesis. That is something important also in the thematic. We can make it fast. We can control the size from nanometers to millimeters, and we can make it in water. Okay, so it's becoming one of the most relevant materials to get transferred to the real application in the real world. Okay. But further than this, we can still make fancy papers with that. We can control the particle size. So once we control this size, this is a work in collaboration between ICN and ICN2 and ICMM. Once we control the particle size with a narrow distribution, we experimentally get this brightness when we recover the material. So first, what is going on with this? Why we have this brightness? And once we get some deposit, we get colors, like real colors. This is visual colors get by a picture, by the eye. So it allows us to access to photonic properties in the same way as Stover particles. Why? Because we can assemble. Once they have the same size, we can assemble in photonic structures that you are used to, probably. And the interesting thing is that they are not Stover, they are not dense, they are porous. So we can host whatever we want now, but we can host different molecules inside or make it empty. And these photonic properties are going to be tuned by the host-get interaction, okay? So opening new parts on the field. This material is selective because our environment is like this, so it's more selective to CO2 than oxygen or nitrogen. So once we have the controls on the particle, we can make tiny nanoparticles of the same size, process as film on top of a chip, means we can integrate our materials in devices. And once we pass a laser, this laser is modified by the host that is entering. In that case, is CO2. So we made sensing of CO2, even though in the presence of water, that is the main competitive, well, it's the problem that we will have if we want to measure CO2, is the selectivity against water. So we can make it until 80% of relative humidity because this MOF especially is really, really, really hydrophobic. Farther than that, MOF are not stable, we all know. But this particularly doesn't look so unstable. So we start moving forward to the application in water environments, really in liquid. I was saying, okay, this is hydrophobic and so on. So it has less problem than the others with the presence of water. But even though inside liquid water is stable for a while, 3 months, 1 year sometimes, depends. And this we just prepare. It's a patent that we have. It's been approved from ICMM, and we start to use that material for contaminant removal or extraction from some metals or so on, or catalytic decomposition. The interesting feature of this material that it was at the beginning unexpected, then we understand, it floats, it generates an interface on top of the surface. So we can recover that material easily from the top of the liquid. And it makes the use of nanoparticles more feasible in the real world. So we will try to move forward together with Pilar to see if we can do something in real with this. As we all know, MOF are not stable to water, but in 2012, people were developing high valence metal organic framework, like zirconium-based, titanium-based, and so on, with benzene linked by carboxylates to the metal clusters. And they say, okay, I put it on a styrene in water, inside water, I collect before, after, I expose to harsh condition, it looks stable to water. And this material that was some of them first prepared on Paris, on the Material Institute of Lavoisier, now that they changed to INS, Sorbonne, they decide to collect water absorption. Okay, it's not stable, but let's collect. It looks like, okay, we have this kind of water absorption isotherms, okay, for 1100 and 1101, and also cycling. Let's make cycling. Let's put water inside, outside, and see what happens. As you see, it's kind of stable, the quantity of water that we can put inside and outside. Sometimes it's not. As you see, this is decaying by cycling, okay? Well, my finger is not, yeah, it's like this. This is UIO66, functionalized by amino groups, and this is 1125, is that one, that structure, that is made by titanium oxocluster linked by terephthalic acid. Okay, so it looks decent enough for the use of vapors and the interaction and the in and out of water inside. And why it's interesting? Okay, there is something that we know for a while, that adsorption is exothermic, as you see here. So there's a visual experiment that we have water in one side, and in the other side we have the adsorbent. So once we put it in contact, if this is a closest universe, okay, that's thermodynamic. This is exothermic process because adsorption is spontaneous. And if it's spontaneous, it's generating hot. It's giving energy, it's giving hot. So if we have a closed system, in one side we have hot, in the other one is decreasing the temperature. Okay? This is the way we make ice in the beginning of the last century. We were using methanol, ethanol, ammonia to make a heat exchanger, to manage the temperature. And we were able to do this. But okay, we start using MOF for heat control. That can be release of heat or decrease the temperature, cooling systems, using methanol or ethanol, because we all know that it was not stable to water. But they decide to measure, especially Janiak and Henningen, they start to make these kind of experiments, and let's see how much energy we are exchanging. So we start with the cooling system and thermal management of this material. Nowadays, it can be one of the first application, of the first MOF that are going to the real application in civil construction, because they are better performance than zeolites and activated carbon. That is the things that we use in the ACs, in the air conditioning systems, and they are in competition with Alpos and so on. But still there. So this thematic that is it moved the end of the last decade, hardly in terms of research, lab research, and now it's in the industrial, almost in the industrial process, for sure in the engineering process, and really close to the real world. Then I need to put something here that I said this material was generated by people in Paris, okay? And I'm always showing that kind of fancy, nice structure and saying we have topological control and so on. But how true is that one? So this is the structure that we have. We have the cluster of metal. We have our terephthalic. This is our representation, our model. This is our pores. But how deep we are, how true it is. So Gauss people in 2020, they decide to make high resolution TEM. What we are seeing here, these are the clusters. Okay, totally aligned, organized, perfectly ordered. And then we have our ligands here. Maybe it's hard to see, but they are copying exactly the crystalline structure that was defined. Why is important that one? Because our simulations are going to be really accurate with the material that we prepare, because they are really the same. Okay. Of course, they are not perfect. They can have defects. But even though that one, we know how to engineer that part. So it starts with the modulation concept. Instead of using a D-topic ligand, we can use a single topic ligand. So it will go only to one point of our structure and not connecting to the other. So it will make a defect. This defect can be a defect of connection here or here. As you can see, we don't have that one. This connection, we have it, here we have that one, no, it's the absence of that, and here we have that, well, sorry, it's this with this. So here we have that connection, here we don't have that connection, we have that connection, okay? So, like this, we can move from FCU topology in UIO 66, that is zirconium based, that one, to BCU, to Rio, or to cubic structure, okay? Coming back to the thermal management, we can make composite, of course. I'm talking about of pure material, even though it's an hybrid material, but we can make composite of this. So in that study, what we decide is to include, okay, we can harvest water, we can take water. So what is taking water a lot? Calcium chloride. Let's put calcium chloride inside our system. We did it, and we break the liquency phenomena of calcium chloride. So our efficient in the exchange of energy, it was 80%. 80% of the heat that we give to the system, it was given back as coldness energy. So they are highly performant exchangers. Also, this material we can process. We can combine with clays, as we are doing at ICMM. And we can use it even though for a heat exchanger with water, or we can use we can put it on the humidificators. The humidificators is another huge application related to water and energy, because we spend a lot of energy in our comfort, human comfort. And human comfort is given by the relative humidity we have in the environment. So we know that in AC we can just ask to extract the water, okay? And it's because we will feel really better. There is a correlation between temperature and water environment, and water in the relative humidity. So like this, we can put it on a fan, we can process, or of course, I was talking about bulk, but industry don't like powder. It has tons of limitation. So to move to industrialization, we really need to process that material. In that case, 2D material, especially clay, could be one option to move it. And I put that one only to show that we can make it in a really huge space-time yield with these strategies. We can make 2 kilo per hour a liter of MOF, but also that to show that here the structure is not the same. As you see, they are changing the peaks. There are some people, first time that afford, okay, you don't have the pure phase. Yeah, we had it. Then I will go in a few to the 3rd generation. We target to make it in sustainable condition, especially in water. So in that 2 works, we focus on the preparation of different families, we call it, of MOF, because somehow we need to group them. So sometimes we group by metal that they are using. So zirconium-based is a super important family because it allows us to make stable materials for water, but also defect control, single crystal to verify really that what we are doing is what we are saying that we are doing. Mil 88 that are iron-based, and cow that is aluminum-based. So they are like metal that are common, and it will become cheap if we can develop it. So we make it at room temperature in different conditions, and also in a semi-continuous way, because we could use spray dryer to spherify the material and get it in a really, really fast time. Then once we assume that this material can be used in water, okay, there are new applications that we can target. I talk about this. Temperature exchange and cooling system based on that phenomena, okay? But we have all the energy that is correlated with movement of ions or batteries and so on. We have new separation phenomena that we can start introducing MOF. We have humidity control, as I say, but I keep that one for the not the end of the water application, but one that is really in the middle of everything, because it deserves a Nobel Prize, actually. So it's water harvesting from air. What means that one? Felipe can tell us a bit more, because he was enrolled in that seminal paper that is from Furukawa and collaborators at Yagi's lab. So first time I see it, I really didn't understand the importance of this, and that they were really keep on that thematic so hard. We were working on the possibility of take water at very low relative humidity, at a controlled relative humidity. So we have 3 main regions. We have really low for heat pumps. We want to put everything inside with the higher energy as possible and heat as much as possible. So we want material that give S shape, we call it, in isotherm. So nothing at the beginning, like this, sharp increase, and then nothing after that. Why? Because then we can make pressure swing in the industry. And with a tiny variation of pressure, we have everything in, everything out. This is cheaper, okay? So we look for this kind of material. So they did it, they made, they picked some, MOF 801, MOF 841. They study until the end where the water was located with neutron diffraction and so on. And then they keep proposing all these tables between 0 and 0.1, 0.1 and 0.3, that will be something like this. That is the regime that we prefer for cooling systems. And then they say, over that one, we always say, over that one, let's go the humidification of the environment. But they introduce something different. They say, okay, if we have this one, we can harvest the water during night, because we are at 25 degrees. And during the day, you know, it's desert, so it's 45. It will go out. Okay, so we can harvest water from the air. And it was like a paragraph in the Jack's paper, so okay, we can harvest water from the air. But they really make it. So they propose some devices, as you can see here. This is in MIT Prepared. They start asking themselves about dew point and all the other problems that you can have. But mainly what they do is to put the MOF in one part, and then a condenser that you do need also. That is becoming the main part, how to condense the water after that. Okay? But they solve it. They put, and then also how to make the light efficient for the heat of the pure material, that the CP, the capacity, heating capacity is really bad. They are polymers at the end with some metals. But they painted in black at first, why not? And then they use a regular condenser there. So they create a company, and of course, the Nobel Prize it deserves in a big part because of that. So it's the main evolution of the company, which is Waha. They are in the 8 million capitalization now of dollars, not much, but enough. And they are creating that devices. I enter on the web page, and they call it Oasis 24, and it's still a future model, okay? But they are really, really close to be able to provide that ones. I think you understand what that means. We can have just a water machine without a connection to anything. Just you push and it come out, the water, of course. This can have military impact, but okay. It's not the only company that it's already there for MOF development. So we have just an example in materials in Europe. It's in UK. It's run by, well, the CEO is one CEO. The founder is one of, is Spanish, he's from Valencia, is David Fairen Jimenez. And what is targeting them? Waha for sure is targeting water harvesting from air. In that part, I didn't say you have two limitations. One is to extract the water directly from the air, and that's done. The second one is to condense it. It's also, I think that is the condenser, that part. Third, if you harvest pure water, we cannot drink it. So you need to put some salt, but it should be easy. In material, for sure, they are targeting something different. Hydrogen storage, why not? Okay, so this is the thing that they are doing different is they can make sort of a similar way to the photonic crystal that I showed you, but they make even more smaller particles, so they are not colored by photonic because they are in the UV range, I think, or in the ER, I don't know, but outside of the UV. But okay, they get monoliths, okay, so they are really densified. So once they take the monoliths, the gravimetric uptake is huge compared to the tank. Okay, so they are preparing their materials, they are optimizing the synthesis, they are targeting that, and they are moving to all gases that you can find, like oxygen. Hydrogen storage is fine, but oxygen is the one that we really expand, and the most bottles of gas that are sold worldwide are oxygen. Why? Because of diving, not dying. Going under the water, okay? You need oxygen. So oxygen is not really easy to study experimentally, so they go computational prediction, and they get the best material, and then they are moving forward in the company to full gases. The modification, I talk fast about this, but I come back because in Kaust also, Daudi prepared that kind of MOF that probably he failed because he want our fancy S-type, and we don't want hysteresis, but he get hysteresis, and not really in the region that it was expected at that moment, but he says something quite outstanding, quite fascinating. They say, okay, my system is passive. I can control the environment because I can put 1 kilo of that one, and over 60% relative humidity, it will take it, and below 30% it will release. Okay, so 1 kilo of the material can control the environment without any input of energy besides the preparation of the MOF. This passive system that, again, when things are very far from the things that you have proposed, we don't realize at the beginning, but there are people that are really checking at this passive system. We put it on the museum. We can protect cultural heritage by the removal of the acetic acid, and also a passive system. Okay, so this is moving in France, not even a company, but it's selling their materials, so they check different materials, and they study how is the absorption of acetic acid besides water that you wanted in the environment. I will try to finish fast. Third generation. So I will try to finish fast because then it becomes really complex. Now we can move the lattice with the host-guest interaction. Okay? So our degrees of freedom are increased. And it comes with MIL53, we can say. Maybe it was, well, in first generation, of course, this is flexibility we can consider, okay? But MIL53 was, they call it breathing MOF, okay? So we can say it started here, the third generation. And they have some feature that, that it can swell. The crystal can physically change because of a change in the topology up to twice, 200%, okay, in size, okay? And it's opening the new pot. We call it third generation because we can have host-guest interaction, and this host-guest interaction make changes on the crystalline structure, at least. But it's not only the only input that we can put. Okay, I will show you after. But now we can stay here. So by host-guest we change, and there are different ways that we can make our flexibility, and then we can have this. We can have that lattice. We put DMF, it conf. We put benzene, it change a bit. Here is a fast, or I don't know, an explanation of how is flexibility given difference in crystallinity. We have a rotation of our molecule that is making a change on the inorganic clusters. So we pass from, we call it narrow pores to large pores, or closed pores, open pores. Well, start a bit confusing, but we have change in lattice. These are a bit more complicated for many reasons. One of them, well, we need to analyze this first. That is not easy in situ all the time. And we have a very close minimum in energy. That is difference is given by the host interaction. But okay, when we try to solve this structure, simulate, you can imagine, we start jumping from here to here. Ramón knows it quite well. So it becoming harder to analyze. So it's the third generation, and the one that, even though if it pop up at the same time as the second, it's coming now to its moment. What is fascinating about this, among other things, is we have this kind of isotherms. As you see, we have one material that should give this isotherm, and then we have another material, because the lattice change. So we jump to here. But okay, it's changing all the time in a reversible way. It's not like the first generation. So defects matter also, and termination. There are a lot of different parameters, especially in the organic molecule, that matters about this. But you can understand that if we have selectivity before, if we can tune also the crystalline structure to accommodate to the host, we can even increase that one. We start calling programmable system, smart material, of course, and so on. It comes also with something in nature, again from Cajal group, with negative absorption. I don't know how much of you are used to that one, but it was really impossible. You cannot have negative absorption. So I don't know how much time they collect that isotherm, how many labs has measured that material before it's published, but it's really negative. Why? Because the contraction is opposite. They are not expanding the pore. They are coming smaller when you have the interaction. So you really go down, and then it go out, and then you come up. Okay, so it's negative absorption. And it's not really on any application, because of course if you want to store gases and you are losing the porosity, have apparently no sense. What we can do with that one is Javier Troyano from my previous group in NanoApp. He say flexibility is nice, but you know, I'm preparing that one, that kind of films with polymers, mixed matrix membranes for separation, with a flexible MOF, but you know, I cannot characterize. It's folding all the time. It's turning all the time. Okay, I prepare this, I go out of the oven, I get this, and then I need to put it again like stiff to collect the XRD, but I cannot. And okay, oh sorry. So he say, I don't mind anymore. Let's make a paper with this. So he start controlling the relative humidity when he understands that has sort of asymmetries inside, and then depending on the relative humidity that he exposed, he has a difference in the rolling phenomena, reversible, and it was coming up, down. So we decide to collect water isotherm to correlate with the phenomena, and also with the crystalline structure at different relative humidity. So here we have an actuator. Okay, it's changing mechanically by an input and output of the host. Then here in Madrid, we are preparing that kind of films. Okay. with our students, and with clays. We combine the MOF with clay, and here you can see the crystal of the MOF is that safe, it's micrometric, but it's totally integrated by the clay inside, so we are trying to solve the structure. The funny thing is we can prepare films, continuous and homogeneous, with the millimetric, with micron-sized crystals that are not easy grace to the clay. But we can do the opposite. Here you can only see the clay, well here also, but in the SEM you only will see the crystal. And we integrate really nanoparticles of MOF almost everywhere. So we deposit, we create these kind of films, and they swell, they change the size in a 91% nowadays. So I'm trying to measure that one, develop, and trying to introduce mechanical movement plus absorption to see if it's contributive or is destructing my temperature exchange, but I think there is 2 contributions now, so it can be enhanced. And of course, it's moving up and down. So the easy thing that we didn't do yet is to put here some silver paste, let it up, down, and close me a system, okay? With the change of relative humidity. And just to end up this story, we are entering in the next generation. That's why the title. It's not clear it's going to be quantum things, quantum MOF, quantum whatever, but it's coming. Something that is, I take that one from this review, so it's a review from 2024. They really call it quantum MOF materials. So just it's a snake peek. I'm trying to give you the pill. This is the new problem that is coming. Okay, we have all these, and then we win. In quantum material, you have that one. These conventional degrees of freedom. We are introducing that other ones. Okay, so now we have interpenetration. I didn't talk about this, but we can create one lattice inside the other lattice. This sort of rhythm, behavior, flexibility. When the host is entering, it will move. Okay, we have something that is rotating, our organic molecules. Meanwhile, we are operating. As you see before, it can be buckling. And we have porosity that in that field apparently is defined by fractality. Okay, so this we can introduce. We have this funny topology that quantum people love about hexagon and the Dirac cone and all my nightmares. So it's changing the band's energy. We can tune it because we can change it, the material, as you see. We can go 2D. I only talk mainly in 3D, but we can prepare MOF in 2D. This is a 2D MOF based on copper. And this is from last year. Nature materials, because it can transport, they call it hot spot. They can transport ultra fast inside the layers. We have ICMM, so for sure ICMM must be here because they are already. They call it QMOF. Bartolome, that is from the Giner Planners group. They published last year what they call it QMOF. I didn't enter, but people that are more used to that kind of quantum material, that are spin here because they put gadolinium inside. So it will come new things for that one, and data storage and other things that will come in. And things that we are doing here, we are working with the understanding of the impact on topology of our bands first, and then try to exploit that one as semiconductor, pure organic semiconductor with the control of the structure. It's submitted R2. We are fighting with the referees. Sometimes they are right, and we need to remake things. We are also seeing some magnetism. Ramón told me, hey, you know that material that that you tell me that simulate that and so on and so on. I think it might be magnetic. I said no. I think it might be. So he simulate each point is a different position of the structure. I don't want to say wrong things. Tons of simulation, some of them are really out of zero in magnetism. So it's magnetic. We are trying to understand, team magnetism is there, Eva is measuring something. Apparently we have something in the real world, and we are processing data, and hopefully we will submit this year to the hopefully journal. And to finish everything, we are trying to make quantum or something like this, but we are coming from here. This is a work that we make on ICMM. We take our crystal, they are photocatalyst in the UV, and we want to turn it to the visible range. So we decide to post-synthetic modify our organic molecules inside the MOF, anchoring different molecules, okay? And we check, yeah, it was changing. It changed to red, from yellowish to really red color. Then we studied the bands, they were modifying, and so on. Once we anchor things, we process as film, and we use it in a photoactive application. So some of us in the field, we are sometimes material scientists, chemical people, chemists, related to condensed matter. Some of them related to crystallography. You are fine, you know the reciprocal world. Some of the others, we are just making synthesis and so on, but we have entered in that mess. So we need your collaboration to develop this quantum stuff. And thanks for your attention.
Thank you very much for the presentation, wide overview of the so many possibilities.
Yeah.
Now it's time for questions.
Oh, fine. Yeah.
So thank you for the talk. Very quick question. What kind of magnetism do you have?
Ferry magnetism? No. Yeah.
So thank you. I just wondering that which are the state-of-the-art techniques for preparing monoliths of MOF? And the second one, you talk about a massive number of applications. Is there anyone that keeping the breaking symmetry is required within a structure?
Yeah. I start from the second, that is easier and shorter. Breaking symmetry in the material, asymmetric materials, you mean? Not sure, because it becomes, this will come to selectivity and so on. Not really. Not really breaking the symmetry, not really. Not an application like only one application. Breaking the symmetry is super relevant. This I'm working a lot for several applications, but in the macro scale. That can be, okay, you have a single crystal of this size and it's breaking symmetries from one side to the other. Diodes effect are super important for application. There are some applications that are coming with diodes effect, but it's coming on the big part of the system, not inside the crystalline structure, because at the end, you have periodicity at the end if you break the, I don't know. And the other thing that is coming is swelling, actuators, and so on. You need asymmetries, otherwise it's not moving. It's just everything is symmetric. But it's from the full system, not from the inside part of the crystalline structure. It's the architecture you made at the end, okay? Yes, in the 3D structure, in the macro scale nanomaterial, we can say. This is coming with the other thing, that how we can make the monoliths. We make it by evaporation, controlled evaporation in a certain relative humidity mold. Okay, Dr. Blade, press. So all the techniques that are classic for the processing of nanoparticles can be applied for this and has been applied. Okay, we keep it on a tube for sure. 3D printing, it's coming like there are a lot of people working. As you see, we can prepare with a spray dryer. If you couple the spray dryer to the 3D printer somehow, electrospinning, so on. So all the processing techniques that are typically used for nanoparticles can be used for MOF and have been used already on MOF. Yeah.
More questions?
Thank you for the talk. My question is very, well, simple.
No.
It is, how is the yield of the fabrication of these materials?
Good
How
question.
is it realistic to have how huge quantities, and which is the price also?
Yes, very good question. One of my students is trying to scale up CIF8 for the patent and so on. So yield, well, the yield, how we define yield is another. So the yield when you go to the atoms regarding zinc is 98%, 98% is fine. Then the molecule is in excess in that case. So we are in mass, I mean, yield from the reaction is 90. If you go to the mass balance, you are in 25%. We are trying to increase. This for this particular MOF. Each MOF has one different story. We are working with Pilar Aranda in the space-time yield, so make it a huge yield and fast. With 1088, that is a flexible MOF, we were in 80% relative yield, okay? And the molar ratio was closer. In that system, we are 110 in metal to molecule. In that other case, we are 1.5, that is the classic, 1.1, 1.5, 1.2, and they are really, really high. So this depends a lot on the MOF. Then prices also depends on the metal and the molecule, okay? CIF8, we were making the estimation. Kilo of ligand is 100 euros in Aldrich, Merck. Kilo of zinc is 100 euros, so we say 100 euros. But then per kilo of reagents. Then it's how we prepare. We are trying to go to a pilot scale to make our prices and so on. Okay, but it can be really, really cheap because this particular MOF it's made in seconds. Then if you wait longer, you increase the particle size, for instance. But and in water at room temperature without extra pressure. Okay, so the price will be really, really cheap. We don't need temperature. So carbon do need temperature, activated carbons. We don't need hydrothermal conditions sometimes. So the price still are on development, but can be really, really cheap. If you go to the one european MOF, one torbium MOF, fancy for everything, luminescent, whatever you want, then it's not gonna be so cheap. Okay, but and also if you take one molecule, we are trying to get molecules from nature, like vanilla has been forever there. No one succeeds, but this MOF that is flexible, 1088, is coming with is made by fumaric acid. Fumaric acid is coming from the cheese and so on. So depends where you take your organic molecule, what metal, it change. But there are group like really hard working on that one. Also targeting to get 100% of conversion, just to don't need to clean it, because then the cleaning is another issue.
Question from the audience? Yes?
Thank you very much for this talk. I would like just if you can comment a little bit about the thermal stability of this MOF, because also the stability for studying the high electromagnetic fields. It's potentially have a lot of power for non-linear optics, but
yeah.
It requires...
For temperature, is quite clear. You have one organic part. So don't heat it over 400 degrees, 500. Otherwise, you go to the carbon, you decompose. Then it's destroyed. Then after 120, you can have some fun. Okay, but depends also in the MOF. They are more robust or less robust. Regarding the magnetic field, I have never seen problems electromagnetic. Yeah, I have not seen much problem with that one. With light, you say it's fine. Depends. If I have one COF that when I impose light radiation, it goes to 600 degrees, like kind of fast. Okay, I use it for heat exchanger that is activated by light. Everything was nice, but yeah, if you really go high in temperature because it's thermo heated, it's heated by light, then you can have problems if you overpass the stability of the material. And then dissipation, they're not good dissipating. This for light, but normally they are quite stable. Depends on the MOF again. And then you need to look the one that are fine or not fine. For the electric field, we use NMR. I don't know if it's, for the electromagnetic, and then we characterize like this, and they survive. If not, we cannot characterize. So this I will not expect big issues. With the potential, I am exposing materials MOF to potential. Up to 10 volts are fine. Over 10 volts, I never try. Okay? Actually, we are trying to move to blue energy, and in blue energy, you start having that kind of events. They look nice for this. But the same, you have electrochemistry there involved, So depends. If you put something that is that you can break, this orange cutting is because we select some molecule, organic molecule that could be cutted by ozone. So can be the way back. Depends. If you put a molecule that can be excited and then is break, then you can play. Or if you put something that is inert for the should be fine.
I have just one more question. So you talked at the end about bringing MOF into quantum materials. If you want to do that and really get quantum technology, so people working on that, having also the MOF as a class of materials that can be investigated in that field, what would you say that are the most important features, characteristics, or properties that they should have?
Oof, I really don't know.
It will be related, for example, to the magnetic behavior. It will be to the possibility of having specific sets of atoms. It could be related to the symmetry also of the systems. Do you have any clue on that? Or maybe we can leave this as an open question
exactly.
and then just hopefully foster also
as
the
far I have seen now,
discussion.
magnetism is quite relevant. Magnetism, spin crossover and all these things. That is really developed because we were there. People were there, actually. But this looks something, this gadolinium stuff and so on. This looks something. This that you really have a magnetic position, splitted. If you have two lines, that one is magnetic in one way, the other is in the other way, and these kind of things I depict. They are looking for, and they are not easily accessible to other materials. Transport and friction and so on is something, but how we rationalize this is hard. And they use copper and they use sulfur groups and 2D for sure in that part, more than the composition that maybe is 2D, and they talk about in-plane, out-plane. So you want something that is splitting the two planes. So 2D MOF can come with something for the transport. Heat transport, electric transport, electron I don't know. This is something I depict also. Topologies, like again 2D. People from the field like 2D. They are coming from graphene. So they like 2D. And hexagons, cagomes, and so on. They are giving some extra features because of whatever mathematics. This, more than the composition that will come after, is pure topology. They are really interested in topology and changing topology. Brooklyn, I don't know why, but they were like, that is not even a flexibility like real flexibility that like transitions, This they like. It might come something that it was a nightmare for us for all the time. This kind of 2D MOF interweaved and everything that you modify with host guest, and then it was changing to several stages and so on, interdigitated and so on. This can be super nice for that. Problem is it's really hard to understand in the first time, so then include all that part. Yeah, and charge, you are working on that. Charge is super important. I think because it's the easiest thing that we can do, So we just start from here. And of course, organic semiconductors come into an era that never happened, but we are getting closer and closer and closer. Yeah.
Well, thank you very much.